Welcome, Hornets. Thank you for joining me today. Today we're going to be taking a look at part 2 of the Chapter 5 practice test number 2. So I'm going to be doing numbers 10 through 15, and we're going to start with number 1. So we're being asked to use the half-angle identity, and we are given a picture. The figure is not necessarily to scale, and we are in quadrant 1. So the first thing I want to remind everybody is that if we are using the half-angle identity, the sign, and you need to see that. Let's make sure you can see my work. There we go. The sign of theta divided by 2 is going to be the plus or minus square root of, and I'm just using the 1 minus cosine of theta divided by 2. Now the plus or minus is referring to the overall angle. And we know that if we are in the first quadrant and we divide the first quadrant in half, we're going to be in the first part of the first quadrant. That's still going to give sine a positive value. As a result, we know that we are working with the positive of this square root. 1 minus cosine of theta divided by 2. We're now going to go to our triangle. We're going to put in our information, 8 and 15, and we're looking at angle theta. Now, according to the Pythagorean theorem, we are looking at our hypotenuse, this opposite side here. I'm going to go hype. The hypotenuse has to equal the square root of 15 squared plus 8 squared. Now, if you do not know that this is a Pythagorean triplet, you will find out very quickly, as you will get a 17, which means that our side is 17 for the length of the hypotenuse. We're then going to find the cosine of this theta. The cosine of the theta has to be 15/17, and this is what we're going to use. Now, some people have expressed some frustration with the half that's happening in the denominator. One way that you can work with this is by putting the 1/2 out in front, and then just looking at 1 minus the 15/17. It's not great, but it does help. We're now going to get our common denominator. This is going to give me 17/17, which I can put all over 17. And then as I simplify it, I notice that the 1/2 multiplied by 2 over 17 is going to give me just the square root of 1/17. I want to make sure that I get the 17 into the numerator as the radical. This is giving me now 17 squared to the square root, and the numerator, and I didn't leave myself enough room, of course, so I will have the root 17 divided by the square root of 17 squared. My answer is therefore root 17 over 17. And this is the answer to number 10. We're now going to go to number 11. Number 11 says use the cofunctions and sum to product formulas to find the exact value of the given expression. The sine of 5 pi over 6 plus the cosine of pi over 3. Now, please be aware you have several choices that you can use, and it becomes your choice which one you're going to do. I'm going to show you both. We're going to start off with the cofunction, and we're going to use the cosine of pi over 2 minus theta is equal to our sine of theta. That means that I will have in the problem, let's just go ahead and write it up at the top, we have the sine of 5 pi over 6 plus the cosine of pi over 3. Now, if I use this right here, I'm going to have the cosine of pi over 2 minus 5 pi over 6 plus the cosine of pi over 3. Now, you'll notice when I get done with this and I use that identity, I'm going to be multiplying by 3 over 3, and I have 3 pi minus 5 pi is minus 2 pi divided by 6 times the cosine, or cosine of negative 2 pi over 6 plus the cosine of pi over 3. Now notice, this is the cosine of negative pi over 3 plus the cosine of pi over 3. Now, according to our even-odd identities, and cosine is an even function, the negative drops away, leaving me with the positive pi over 3. We know that the cosine of pi over 3 is 1/2, plus the cosine of pi over 3 is 1/2, and we get 1 as our answer. Let's look at what happens if we decide to change the cosine of theta into the sine of 90 degrees, pi over 2, we're in radian mode, pi over 2 minus theta. If I put this in, I end up with the sine of 5 pi over 6 plus the sine of pi over 2 minus pi over 3. Now that means that I'm going to have to multiply this pi over 3 times 2 over 2 and the pi over 2 times 3 times 3. This is going to give me the common denominator of sixths. And I will have 3 pi minus 2 pi all over 6 plus the sine of 5 pi over 6. I now have the sine of 5 pi over 6 plus the sine of pi over 6. Now, because the question was asking us to use the sum to product, this is the one that is most likely desired. Notice right here, the cofunction immediately gives me an answer without working with the sum to product or product to sum. But if I have this, I'm now going to need to use my sum to product, and I'm now going to work with, let's see, which formula is it? Here we go, is right here. Sine of 2 times the sine of the first angle plus the second divided by 2 times the cosine of the first angle minus the second divided by 2. So that's the one I'm going to work with. And I'm now going to have 2 times the sine of 5 pi over 6 plus pi over 6 divided by 2 times the cosine of 5 pi over 6 minus pi over 6 divided by 2. When we add, we get 5 pi over 6 plus 1 pi over 6, we get pi. So the sine of pi divided by 2 times the cosine. Now you'll notice when we do this, once again, it might be easier to think about it as 1/2 times 4 pi over 6. Notice that's the 5 pi over 6 minus 1 pi over 6. This will give me 1/2 times pi over 3, and 2 pi over 3, and I end up getting a pi over 3 when I simplify it. So I have the cosine of pi over 3. Well, we know that the sine of pi over 2 is 1, and we know the cosine of pi over 3 is 1/2. 2 times 1/2 gives me 1, and that is the same solution we got from our first cofunctional identity. Be aware, this is a little bit more difficult, and if you are asked to work with the product to sum along with the cofunctions, you're going to have a little bit more work to do. All right, let's go ahead and go to the next question. Our next question is asking us to find the exact value, and we're trying to find the exact value of cosine 2x equaling cosine x. Now to do this, I worked with my identity, and I'm going to have to decide which one I want to work with. And I seem to have lost that page. And it should be somewhere around here. Oh, great. Alrighty, let's go ahead and do it again. I was hoping that I wouldn't have to do it twice, but it appears I am going to have to do so. So the first thing that I'm going to do is recognize which problem do I want to work with. And let's see which one we have. So we have cosine of 2x equaling the cosine of x. Alrighty, well, let's go ahead and use the cosine squared. Let's use this one right here. I'm going to then have a quadratic, and with the quadratic, I'm going to factor it, and let's see what we get. Putting it in, I have 2 cosine of squared of our x minus 1 equals the cosine of x. That means that the cosine squared of x minus the cosine of x minus 1 is now equal to 0. I'm going to factor this using the cosine of x. I know I have a 1. Cosine of x, I know I have a 1. In order for me to get a negative, I'm going to have a minus there for the minus 2 cosine and a plus to have a positive 1 cosine. That means that the cosine of x is going to equal negative 1/2, and the cosine of x is going to equal positive 1. Now remember, if you have problems factoring, I recommend you use the dummy variable cosine of x. This will give you 2u squared minus u minus 1, which most people will be able to factor. Once again, you always look for an easier way as opposed to trying to just bully your way through things. It's not going to help. Notice I can then immediately go to u equaling negative 1/2 and u equaling a positive 1 and then back substitute. And notice I end up getting to the same place. So please, always look for the easiest route. Don't make your life so hard. The world is hard enough. We don't need to make it worse. That's not what we want, so we don't. Now I'm going to go ahead and I'm going to find my solutions. We know cosine is 1 at 0 pi, and we know that cosine is going to be negative 1/2 in the second and the third quadrant, and the reference angle is a pi over 3. So I'm going to have 2 pi over 3, or 0 degrees, let's try that again. 120 degrees, we have 0 degrees, and then in the third quadrant, I'm looking at 4 pi over 3, and that's going to give me 240 degrees. And the reference angle is a 60-degree angle. Now, when I look at this, the reason why I went into degrees is because I noticed that the domain is from 0 degrees to 360 degrees. Be aware, I am going to check my answers. So if I put them in and I get the cosine of 240 degrees, and I know that that's a negative answer, and it's equivalent to the cosine of 240 degrees. They have to be equal. If I put 240 degrees in, that's going to give me 480 degrees minus 360 degrees is 120, which is also the negative 1/2. When I put in 240 here, I get negative 1/2 as well, and it's the same. If I plug in 0, I get cosine of 0, which is 1, and I put the cosine of 0, which is 1. So all three are correct solutions, and I have found my answer. This is going to bring me now to the next question. And the next question is asking me to solve the sine of x equaling sine of 3x. Once again, we're just going to go ahead, and I'm just going to go ahead and do it. Here we go. Keep in mind that this one's a little bit more difficult, and that's because we are going to be looking at having a lot of different substitutions. So I'm going to start with the sine of x equaling the sine of 3x. Now, this one is going to have to work by using my sum addition, the sine of 2x plus x. Now, I've asked you to memorize this formula, so you're going to have to just put it in as the sine of 2x, cosine of x, plus cosine of 2x, sine of x. I now have to figure out a nice and reasonable identity to replace, and I have this one as my double angle identity. So the sine of x is equal to 2 sine x cosine x times cosine x, plus, and I'm now going to have to use one of my double angle identities for cosine, And the one that I'm going to work with is the one that uses the sign. So 1 minus 2 sine squared x. Once again, we're going to put that in right here. This is going to give me 1 minus 2 sine squared x times sine x. Alrighty, I now have sine of x equals 2 sine of x cosine squared x plus sine of x minus 2 sine cubed x. I'm now going to look at this piece and I'm going to replace it so that everything is in terms of sine. Sine x is equal to 2 sine x, 1 minus sine squared x, plus sine of x minus 2 sine cubed x. I'm now going to distribute. Sine of x equals 2 sine of x minus 2 sine cubed x plus sine of x minus 2 sine cubed x. Alrighty, adding like terms. Sine of x is equal to 3 sine of x minus 4 sine cubed of x. I'm now going to move everything over to the left. So everything's going this way so that I can get this cleaned up. 4 sine cubed x is now minus 2 sine of x is equal to 0, which means I can now factor a 2 sine of x, leaving me with 2 sine squared x minus 1 equals 0. Well, that means that 2 sine of x is one factor. I'm now going to factor this into the difference of squares, plus 1 and minus 1. And now I'm going to solve. 2 sine x, I want it to equal 0. This will happen at 0. And let's just make sure we are in radian mode. So 0 pi and pi. I'm then looking at the sine of x is equal to, you'll notice I get negative 1 over root 2, which is negative root 2 over 2. Sine of x is going to then be the positive 1 over root 2, which is root 2 over 2. And I now have several solutions. This one would be in the third quadrant, 5 pi over 4. And we're looking at 7 pi over 4. And then in the first and second quadrant, I'm looking at pi over 4 and 3 pi over 4. I'm now going to want to check all of my answers. So I'm going back to the original. 0, sine of 0 pi is 0. Notice 3 times 0 still gives me 0. So 0 is equal to 0. Plugging in pi. Sine of pi is 0. Sine of 3 pi is still 0. It is coterminal to pi. So both of these are going to work. I now have to look at 5 pi and 15 pi, and I'm going to subtract 8 pi, leaving me with 7 pi. Notice those two are negatives, and that is true. So we know 5 pi over 4 works. 7 pi over 4, 21 pi over 4, taking away 16 pi over 4, that's 2 full rotations. We are at a coterminal, which is equivalent to 5 pi over 4. And once again, both of those were equal. Now we go to pi over 4 and we plug it in. Pi over 4 and 3 pi over 4 are both equivalent in the first and second quadrant. 3 pi over 4 is next. We put in 3 pi over 4. We're looking at 9 pi over 4 minus 1 rotation, which is 8 pi over 4. Leaves me with 1 pi over 4. Once again, the first and second quadrant are equivalent. All of the answers are correct. All of them worked. And my solutions are 0 pi and pi, 5 pi over 4, 7 pi over 4, pi over 4, and 3 pi over 4. Ta-da! And that is that problem there. That was number 13. Now the next problem that we have to work on, that actually gave me a little bit of a stretch, and I ended up having to do considerable amounts of work in order to do it. Now that was because I had to try all of my different identities as I was going through and trying to figure out what's going to work best for me. So be aware, you're going to have to try things out. You're going to have to just check and see if it works. So I have tangent of x over 2 plus the cosine of x equaling 1. This was our next problem. Make sure I get that out and show it to you. There you go. It's in radian mode, so I'm going to have to work with this in radian mode. Here we go. Take a deep breath, and remember, I've already done this problem 3 different times using each of my identities in order to figure out the correct identity to use. Let's just show you what we have. We have either the plus minus square root of 1 minus cosine x plus 1 over cosine x, sine x over 1 plus cosine x, or 1 minus cosine x over sine x. Now, I found the easiest identity to work with was the sine of x divided by 1 plus cosine of x. Cosine of x. Now, because I'm using a cosine, I brought this 1 over so that it equaled 0. I then wanted to get the common denominator. So I have the sine of x over 1 plus the cosine of x plus cosine of x minus 1 over 1 times cosine of x plus 1 over the cosine of x plus 1, still equaling 0. Now this gave me the sine of x plus the cosine squared x minus 1 all over 1 plus the cosine of x, equaling 0. I then recognize that this is the opposite of the Pythagorean theorem, which means that I'm going to have to factor out a negative. Sine of x minus. Now I have 1 minus the cosine squared of x divided by 1 plus cosine of x equaling 0, and I now use the Pythagorean identity, making this the sine squared of x. Sine of x minus the sine squared of x divided by 1 plus the cosine of x. Now the only real issue here is when I find my answers, I have to make sure that I do not get an asymptote or a 0 in the denominator. That would cause a problem. So I'm going to have to go back and check my answers and make sure I eliminate anything that creates a 0 in the denominator. Here we go. I now have sine of x, which I can factor, into 1 minus sine of x, equaling 0. Notice it's only the numerator that I'm going to make equal to 0. That means that the sine of x equals 0, or 1 minus the sine of x equals 0. If that's the case, I want 1 equaling the sine of x. Now we know that 0 is going to happen with the sine of x at 0 pi in radians and at pi. When I work with this one, I know that the sine of x equaling 1 occurs at pi over 2. So these are the ones I'm going to check. Notice that if I try to put a cosine of pi, I get negative 1. And 1 minus 1 is 0. I am going to eliminate pi straight off the bat because it creates a 0 in the denominator in the identity that I've created. I'm now going to check both answers. I'm going to plug them back in. So I have 0 over 2 for the tangent. We know that the tangent of 0 degrees, or 0 pi, is 0. The cosine of 0 pi is 1, and 0 plus 1 makes 1. 0 pi works. We're now going to put in pi over 2. Tangent of half of pi over 2 is pi over 4, and the tangent of pi over 4 is 1. The cosine of pi over 2 is 0, and 1 plus 0 is 1. pi over 2 will work. I now know that the two solutions are 0 pi and pi over 2. That is my answer to number 14. That leaves us with only one more problem to work on, and that is trying to verify that the tangent of the arc sine of x plus 2 over 8 is equal to x plus 2 divided by the square root of 64 minus x plus 2 squared. Let's go ahead and now take a look at this one. I'm going to start off just writing down the problem again so that I can reference it easily while I'm doing my work. I want to show that it is x plus 2 divided by the square root of 64 minus x plus 2, the quantity squared. Now we know that we're going to assume that this is in the first quadrant, all right? So just be aware, I'm assuming it's in the first quadrant. That means that my hypotenuse is 8 and my opposite side is x plus 2. By using the Pythagorean theorem, we know this side A has to be the square root of 64 minus x plus 2, the quantity squared. And I can then find the tangent of this theta, and tangent of our theta is the opposite over the adjacent, x plus 2 divided by the square root of 64 minus x plus 2, the quantity squared. Notice we have now set it equal, it has worked, and we are done. That is part 2 of the second pretest for chapter 5, and I hope this has helped. Please feel free to play it as many times as you need it so that you get good at seeing and recognizing how we are using our identities that we have here and that we have here. Okay? Once again, you need to know how to work with these identities, as I will not be giving you the sum difference or the sum identities and the difference identities, and I won't be giving you the double angle identities. I will give you the half angle. I will give you the product to sum and difference in both ways. So this way and this way along with that. Okay? So just a reminder, you do not have to worry about memorizing these or these down here. Okay? Alrighty. Thank you very much, Hornets. I hope this has helped. Please remember to click like if you found this useful, and I hope you have an excellent day. Take care and be safe. Good night.